Okay, so yesterday we had started with the definition of work done by a force, and we saw that the work done can be defined by a very simple definition of dot product if the force is constant, and the definition becomes a little bit more complicated. It becomes path integration of force over the displacement from initial to final position if the force is variable. So let us look at an interesting example of that today. So in this example, what's happening is that we have like this hemispherical surface, okay, which is going to be smooth. So this is a smooth hemispherical surface. Of radius r. Now a particle is released from this position, and once it is released, because of gravity acting, it will come sliding down to this position eventually. Okay, so a particle P of mass 5 kilograms slides from A to B. So now given that this theta is 53 degrees, the radius is 10 meters, the acceleration due to gravity is 10 meters per second square. We want to find the work done by gravitational force on it. And the normal reaction force. So just try out this question. Okay, I have received your answers. Now let me explain how this will work out. Most of you have said that work done by normal reaction will be zero, and that's correct. Very good. But the work done by gravity, how we'll calculate? Let's look at that also. So we have to use two different concepts for calculating the two different work done, because normal reaction here will be a variable force. That's the point. No? Normal reaction will not be constant as the body moves or as the particle moves, because its direction is continuously changing and so will its magnitude. But gravitational force, on the other hand, that will be a constant force. So as this particle is moving from the initial position where theta is 53 degrees, now let us say, so this is at t equal to 0, it's starting from here, then it's reaching here. But let's say at some intermediate time, it is at some intermediate position like this. So when the particle is here, if you look at the forces acting on it, there will be the normal reaction force, which is acting directly towards the center point, because it will act normal to the surface. So it will act such that it's directed towards the center of curvature. Okay. And then there is the gravitational force, or mg, which will act vertically downwards. So if you compare this with this other position, you can see that mg is not changing, but normal reaction keeps changing its direction and also changes its magnitude. Now, if you compare this with the immediate differential displacement, so that is along the tangent. So the ds vector will be always along the tangent to the circle at that point. Okay. So this angle is always 90. So what happens is mg is a constant force. Okay. So work done by mg we can calculate by the dot product method. Okay. But normal reaction is a variable force. So work done by normal reaction has to be calculated by integration of normal reactions dot product with displacement. Okay. But then at the same time, what helps us out, okay, and we don't actually have to do any integration end of the day, is that normal reaction acts perpendicular to the surface. So that means it's pointing to the center of curvature at all times. And the differential displacement at any instant is tangential along the tangent to the surface at all times. Okay. So therefore what happens is that this quantity n dot ds will be 0. So work done by normal reaction will therefore become 0. So that's done. Now, as far work done by gravity is concerned, we have to just work out this dot product mg dot s. Okay. So you have to figure out this displacement and the vertical's gravitational forces dot product. So the displacement will be this vector as the particle moves from here to here. And mg will be like this. Okay. Remember, radius was given to you as 10 meter. Okay. Cos theta, yeah, where this angle will be the theta you're talking about. Okay. But the easier way to do this is just break this in components now. Take this as your xy axis. So you can see that this term is y, suppose, and this term is x. So write the displacement vector as minus xi cap minus yj cap. In the diagram, you can see that x is r sine 53 and y is r minus r cos 53. This will be your displacement. And the mass of the particle was 5 kgs, I think. Yeah, 5 kgs. So mg as a vector, we can write as minus 50 j cap in newtons. This is the easiest way to calculate the dot product. Understood, Ansh? Yeah, 2r by 5. So this will become okay. So now you see work done by this is how much. So substitute this information here. So plus 200 joules. That will become the work done by the gravitational force. Okay, so the component part is like this. See, you're moving on a circular track now. Okay, so we are moving on this circular track from this point here to this point here. Okay, so our displacement vector is this. So to calculate this displacement vector, what we'll do now is we'll drop a perpendicular here from this point onto this. So drop this perpendicular and then look at the trigonometry of this triangle now. So this side is y, sorry, this side is x. And this side is, let's say, some base b. So b by r is cos 53, which is 3 by 5. And x by r is sine 53, which is 4 by 5. Okay. And now for the displacement, we are looking for this component y. So y is, you can see, r minus b. So that is r minus r cos 53. Because again, this whole thing is r now. Okay. So now your displacement vector is very clear in the diagram. The displacement vector has a negative x component x and a negative y component. So that becomes okay. And next just substitute the value of r and the value of sine and cos. Is it clear now? Actually, you don't even need to calculate the x component because after the dot product, the x component will not be significant. It will be only the y component. Okay, so hope you have all understood this question. Now next we'll move on to the relationship between work done and kinetic energy. So this is very important. So this is called the work kinetic energy theorem. So the statement of this theorem is that the net work done by all forces acting on a body equals to the change in its kinetic energy. Okay. Or as an equation, it can be written as something very simple, that net work done is equal to the change in kinetic energy, where this net work done is the algebraic sum of work done by all forces acting on the body. Okay. So if we have a body on which there are a number of forces acting, then net work done is okay, where like this. Okay. And on the right hand side, the change in kinetic energy, so that will be defined as the final kinetic energy minus initial kinetic energy. Which will become half mv square minus half mu square, where v is final speed and u is the initial speed. Because as you know, we define kinetic energy by the equation or by the formula half mv square, where m is the mass of the body and v is the instantaneous speed. And kinetic energy is also expressed in joules when m and v are taken in SI units. Just make a note of this theorem first. We'll discuss more about it. Work done is a scalar quantity, Ansh. That is why when we say net work done, it is the scalar algebraic sum. It's a scalar quantity which can be positive or negative. Okay, so net work done by the forces acting on a body, that's why it becomes the algebraic sum. Okay, so eventually we will look at the proof of this theorem also, but let's start by looking at an application example. So let's look at an example of this. So we have this situation now. We have a rough surface which has a coefficient of friction equal to 0.5, and this block is initially at rest. Now we start pulling it with a constant force. But that force is applied in this manner. A constant external force F is applied like this. So the block of mass 5 kilograms is pulled with a constant external force of magnitude 50 newtons, acting at an angle of 37 degrees to the horizontal. Now we want to find out that by the time this block reaches this position here, what its speed becomes, given that its displacement is s. So we want to find its speed v at a displacement of 20 meters. Okay, so I'll take you back to that, don't worry, the work energy theorem. So if you finish that, then start working on this question. So what we want to do here is we want to apply work energy. We will do this question by application of this equation, that the net work done should be the change in kinetic energy. In this case, the net work done will be the work done by all the forces, F plus the work done by friction plus the work done by mg plus the work done by normal reaction. Okay. And the change in kinetic energy will be half mv square, because u was 0. So the initial kinetic energy was 0. So just try this out. You can also, of course, just find the acceleration of the body using Newton's laws, because it's a uniform acceleration, and then use kinematics. But then that's two steps. No? First, you will have to use Newton's laws, resolve all the forces, find the acceleration. Then second step, you'll have to use the relation that v square is equal to 2as. Whereas by work energy theorem, you can do this in a single step. Okay, so let us work out the calculation. Yeah, Tandresh, I've got your answer. I've got the answer from Ansh also. I think both your answers are correct. We just check. So you'll still have to make the free body diagram because we need to calculate the frictional force. So this F, which is 50 newtons, which is acting at an angle of 37 degrees. We have to break this into components. F cos theta will become 40. F sin theta will become 30 newtons. Okay. Mg is 50 newtons because the mass is 5 kg. So your normal reaction will become how much? The normal reaction will be mg minus F sin theta. So that will be only 20 newtons. So friction, accordingly, the kinetic friction which is acting on the block, that will be equal to mu n. So mu was 0.5, so that will become 10 newtons. So the kinetic friction acting here will be equal to 10 newtons. Okay. Now under the action of all these things, the displacement that the block is having is in this direction. The displacement vector is like this. Okay. So work done by F. Okay. This will become Fs cos 37. Okay. So the S was how much? It was 20 meters. So this will become 800 joules. The work done by normal reaction will be 0. The work done by mg will be 0 because they are perpendicular to displacement. Each of these forces are perpendicular to displacement. The work done by friction will be how much? Minus of friction into, so when you take the dot product now, the minus sign will come in because it's at 180 degrees. So it will become minus, much is it, 200 joules. Okay. So these are the work done by each of the forces. So next what we'll do is we'll calculate the net work done as the sum of work done by each, by all four forces. So that will come out to be plus 600 joules. So that net work done is equal to the change in kinetic energy. So 600 joules is equal to half mv square. So v will become square root of 2 into 600 divided by 5. So square root of 1200 by 5 or 240 newtons. Okay. Sorry, 240 square root meters per second. So then we can factorize this. 240 we can write as 4 into 4 into 15. Which will become approximately almost 16 meters per second, less than that. So square root of 15 we can approximate as 3.87. So as I said, it will be okay. Yeah, it can be pulled by a string, it can be directly pulled also. That doesn't matter. Okay. So maybe there is a thread attached like this. Okay. And we are pulling the thread with that force. So that is creating the tension. Can be like that also, or we can be directly applying the force also. As an external agent, we could be directly applying the force at that point. अरे एंगल 90 है ना बेटा, यहाँ पे आपको दिख रहा है ना कि नॉर्मल रिएक्शन इज एक्टिंग लाइक दिस एंड द डिस्प्लेसमेंट इज लाइक दिस. Okay, similarly mg is acting like this. These are all constant forces here, no? Okay, so hope this question is clear. Yeah, so next we will move on to the doubts. So Tantresh and who else? Somebody else, you have the doubts from the common test. So if possible, can you send me the picture of the questions which you have doubts in? Yeah, Ansh. Ansh and Tantesh, you are having questions from the common test. Can you please send me the pictures of the questions on WhatsApp? Cumulative test, sorry, not common test. Okay. And apart from that, if anybody has doubts from friction, please send me those also. I will start with the doubts now. So if you have doubts from the module exercise or HC Verma, please send me the question number on text message. Whereas if you have doubts from the the cumulative test, please send me the photo. Yeah, so I'm receiving these questions now. Okay, so I'm starting with this question now. From cumulative test question number 2, it says a rope of mass 5 kg is moving vertically in the vertical position with an upward force of 100 newtons acting at the upper end and downward force of 70 newtons acting at the lower end. We have to find the tension at the midpoint. Okay, so we have this kind of situation that we have this rope kind of thing. Now this has a mass of 5 kg, so it's a heavy rope and it's in the vertical position, and we are moving it in that vertical direction by application of one force at the uppermost point, which is 100 newton acting at the upper end, and another force of 70 newton acting at the lower end in the downward direction. So we have to find the tension at the midpoint. So if the midpoint is C over here, to find tension at midpoint C. Okay, so what we'll do here is we'll first make the free body diagram of the entire rope and understand its acceleration. So FBD of the full rope. So let's say this end is A, this end is B. So just imagine, so on the full rope, the forces which are acting are F1, F2, and the weight. And this combination is giving the upward acceleration A. So F1 minus F2 minus mg is equal to ma. Okay, so 100 minus 70 minus 50 is equal to, now interestingly, this is giving us an acceleration which is negative minus 4 meters per second square. So minus actually means that the acceleration is downwards. Okay, so we have to change this to an acceleration now which is downwards. Okay, and that downward acceleration is 4 meters per second square. Now next thing, to find the tension at the midpoint, we will make the free body diagram of half the rope. Okay, so make the free body diagram of either AC half or CB half. Either way it's fine. Okay, we'll see both work. Only now this is A downwards. Okay, so if you make of this section AC, then what are the forces acting on it? There is F1, there is half the weight, okay, and there is some kind of tension at this midpoint, and that combination is giving it an acceleration of 4 meters per second. If you make the free body diagram of this part CB, then what are the forces acting on it? There is tension at the midpoint acting upwards on it. Now, the upper half is pulling this the upward direction. There is a weight of that half rope, which is m by 2 to g, therefore, and there is this force F2 which is acting on it. This combination is giving the same acceleration. So I can do either this or this. That will be enough because I just need one thing, the tension. So in this, it will become F1 minus this half weight minus tension is the mass which is m/2 of that section into A. So from this equation now I can substitute A and I can get the answer. So F1 was 100 newtons, half the weight is 25 newtons because the weight was 50 newtons, right? Minus this unknown tension should be equal to, oh sorry, it's downward, my mistake. The acceleration is downward, so the net force should be taken in the downward direction. So it's the half weight plus this tension minus F1. So this half weight is 25 newtons, okay? Tension is unknown, F1 was 100 newtons. So this should be 2.5 into 4. So let's see what this gives us for the tension. So 10 plus 100 minus 25. So the tension at the midpoint according to this should be 85 newtons. And you will see that this one will give you the same thing. If you write the equation for this one, you will get F2 plus this half weight minus tension should be this mass into A. So 70 plus 25 minus TC should be equal to 2.5 into 4. Okay. So 95 minus TC should be equal to 10. So this will give you the same. The tension at the midpoint is 85 newtons. So hope this is clear, Ansh. Oh, sorry, this was not your doubt. So, Tantrish, I think this was your doubt then. Is it clear? Okay. Yeah, Ansha, I will come to your doubts. Okay. We complete these two. So, anyway, hope this question is clear to all of you. So, next is question number 13 from the same cumulative test. This is also sent by Tantrish. This is a 10 kg block. This is a 5 kg block. Here the coefficient of friction is 0.3. Here the coefficient of friction is 0.1. Now we are applying force on this block like this. The force is shown on the other side, but it's the same thing. Both are initially at rest. So if F is equal to 15 newtons, F is equal to 15 newtons, you have to find out what happens. Take G as 10. So, excuse me. So you can see that on the 10 kg block, the moment we apply force like this, there is some friction acting like this. And that friction's maximum possible value is mu1 into 10g. So that is how much, that is going to be 10 newtons. And now on the 5 kg block, we will see that this friction will act like this. There's some friction from the ground which is possible. Now F2's maximum value will be mu2 into the combined weight. No? So that's 150 newtons into 0.3. So that's 45 newtons. Okay, now you can see this that F1's maximum possible value is only 10. Whereas this one's maximum possible value is 45. So that means the block 5 kg block can never move. If this is the block B can never move because there will always be static friction available on the ground. So this is showing you that since F2 max is greater than F1's max, therefore 5 kg block cannot move no matter how much force we apply on the 10 kg block. So here what will happen is, so when we apply this 15 Newton force, okay, it is exceeding the maximum value of 10 Newtons. So this one will move. So this one will move because F is greater than F1 max. But this one will remain at rest with F1 max equal to 10 Newtons acting on it. Okay. And F2 static friction will just balance F1. So 10 Newtons will act on it. Okay. And this acceleration will become F minus F1 kinetic friction will be equal to mass into acceleration. So 15 minus 10 become 10 a. So this acceleration will become 0.5. Okay. So now we know what's going to happen when we apply this force of, when we apply the force of 15 Newtons. Okay, this block A will start moving at 0.5 meters per second square, but B will remain at rest. Hi. Okay, next Ansh, I'm moving to your doubts. This is question number 11 from the same cumulative test. So let's finish maximum doubts from the cumulative test today. So we have this kind of rough inclined plane problem. Okay, 37 degrees. This block is of mass 10 kg. This block is of mass 5 kg. And the coefficient of friction is 0.5. Okay. So we have to find the blocks are in equilibrium. So you have to find the frictional force. So if the blocks are in equilibrium, you can see that the tension here should balance the weight. Okay, so for equilibrium, so 50 newtons of tension should be acting. So now when we look on A's free body diagram, now we can see that A's weight has a component in this direction. So that will become how much? It will be 100 cos 37, sine 37. So that will be 60 newtons. Okay. Whereas the tension from the other side is how much? It is 50 newtons. So A being in equilibrium, it has a tendency to slip down like this. So static friction will be acting like this only. So for the block A, you can see tension plus static friction will balance weight's sine component. So substitute the tension here. So 50 plus this should be equal to 100 into 3 by 5. So static friction's magnitude will come out to be 10 newtons and direction will be up the inclined plane. And you can see that that much static friction is available because maximum possible friction is equal to mu n. So that is 0.5 into 100 into 4 by 5. So up to 40 newtons is available. Okay, but only 10 newtons is required. So there's no problem with this. So the system will be in equilibrium. Is the question clear, Tantrish? Okay, let's move on to the next one. Ansh, yeah. Is the question clear? Okay, now the next question. Okay, so this is like this now. Okay, so the block B moves down with a velocity of 10 meters per second. So we have to find the speed of block A. So here we will use the concept that if you look at the block B, the net tension acting on it is 2t upwards, and its downward velocity is Vb. So power delivered by tension on the block B will be minus 2t into Vb. Okay, because tension and velocity are in opposite direction. Now on the other hand, on the block E, what is happening is that the tension is acting in this sort of direction. Whereas the velocity of block A will be this vector such that this angle is 37 degrees. So the power delivered by tension on block E is the dot product of these two. So it is TVA cos 37, or that is 4 by 5 PVA. Now the net power delivered by tension, because it's an internal force in the system, that should be 0. So net power will be the sum of power delivered by tension on A plus on B. They should be 0. So this equation tells us that okay, so this is the shortcut method of doing the question. Now you are also supposed to do the question by calculus method, which I will show you, by using thread length conservation, but you can note this down as a shortcut method first. Okay, this is the shortcut method. Okay, using the fact that net power by tension is equal to 0, because tension is an internal force in the system. Okay. You'll also understand this power better when we discuss about power in the current chapter we are doing, which is work by energy. But the fundamental way of doing it is by calculus, which we'll look at next also. You can also use the calculus method and conservation of thread length. So we will look at that method also. But since we are doing work by energy right now, note down this method. This will be like a shortcut method for us. Okay, so let us look at the calculus method of solving this. So in this particular test, you are supposed to solve it by the calculus method. Okay. So in that, what we'll do is we will express the thread length So let's express this distance, this vertical distance as y, okay? And let's express this distance as z. So also this distance can be expressed in terms of the sum of, the hypotenuse of these two. So this is x and this is y, okay? So because thread length is constant, that means 2y plus z should be a constant. Okay, because the thread is going around this, right? So it has two vertical sections and this. That's proportional to the total thread length, so it should be constant. Okay, so that means 2y plus square root of d square plus x square is constant. Now, if this block is moving like this, so you can see that x is decreasing at the rate of VA. So we'll write dx by dt as minus VA. Whereas if this block is moving like this, then y is increasing at the rate of VB. and small d is constant, of course, because this is just the height of this from the ground, so that's fixed. So now what we'll do is we'll differentiate this equation with respect to time t. So for differentiation, this is the plus differentiation with respect to time of this thing, d square plus x square. So this is where we'll use chain rule, and on the other side this is 0. Okay, so 2 times dy by dt plus, now apply chain rule. So differentiation of square root function is 1 upon 2 times square root function into differentiation of this. So it becomes this whole term. So this is 0. So ultimately we get this relation that 2 dy by dt plus x upon square root of x square plus d square into dx by dt is 0. Just give me 2 minutes now, I'm coming. Okay, now use this over here, and also use the fact that if this angle is theta, okay, then your x upon root of x square plus d square, nothing but base upon hypotenuse, so it is cos theta. So you'll use this also. So this equation will become like this, that minus 2vb, oh sorry, plus 2vb plus cos theta into minus va is 0. So va cos 37 degrees is equal to 2 times vb, because theta was 37 degrees. Okay. So this is the fundamental way of solving the question. It's a little bit lengthy, but it's an application of differentiation, and you have learned differentiation as part of the preparation of this test. So that is why it was there in the test. But in future, we will be using the shortcut method, which I showed you today, which is the fact that the net power delivered by tension should be 0. Note this down quickly. Okay, so Ansh, hope you understood this question and also understood the chain rule application step here. ये जो differentiation किया है ना, this is by the chain rule method. So actually what we are doing here is first we are differentiating this with respect to x and multiplying that derivative with dx by dt. And then when you are doing this differentiation itself, there is a chain rule application here. So this differentiation itself becomes like this. Okay, good. So we'll discuss the remaining questions also, but we'll have to keep some of them for the next time. Out of the questions you sent to me, there's one question I want to discuss right now only, next couple of minutes, whereas the other questions we'll keep for next time. So that is question number 24. So that is like this: you have a block which is kept in equilibrium like this by connecting it to a spring on one side, which is like this, and a thread on the other side, which is like this. And this angle that the spring is making, it is 53 degrees. Then what we are going to do is we are going to cut the thread. So when we cut the thread, the block will develop some acceleration. So we have to calculate the acceleration. So make the block's free body diagram. So there will be spring force acting on it, which is kx naught, let's say, because right now the spring is extended by x naught and has a constant k. There will be some tension in the thread T, and there will be weight mg. So it's in equilibrium. So this angle being 53 degrees, you can see that kx naught cos 53 degrees balances mg. So 3 by 5 kx naught is equal to mg. The first equation. And kx naught sine 53 degrees balances the tension. So tension is equal to 4 by 5 kx naught. That's our second equation. So when you substitute this, you will get kx naught is 5 by 4 mg, and the tension is 4/5 of that. So it is 5 by 3 mg. Kx naught is equal to from the first equation, kx naught is 5 by 3 mg, and from the second equation, it is 4 by 3 mg. X naught is the extension of the spring. X naught is the spring will be in extended state. No? L is the natural length. Understood now? Okay. Now what will happen is the moment we cut the thread, at the instant the thread is cut, okay, tension becomes 0, but x naught is the same. So that means the force kx naught is the same. So what will happen is that at that instant, instant, just at the moment when you cut the thread, these are the forces acting. There will be Kx not acting at that same angle of 53 degrees, and there will be mg acting. So this block will have an acceleration in some kind of direction like this, which is the vector sum of these two. So the net force will become the vector sum of Kx naught plus mg, and that will become equal to mass into acceleration. Okay. So now we can either use component algebra from here and work it out, because the spring's length doesn't change immediately. No? It will take some time for the spring to compress. No? It can't change suddenly from x naught to a different value. You understanding? So this is the same because the spring remains in same state at that instant. Doesn't change its state immediately. That's why. So we can break this into components and understand. So this will be Kx naught sine 53, which from above was equal to the tension. So that was equal to 4/3 mg. And this is Kx naught cos 53, which was equal to mg. Okay. From these. And this is mg. So the net force on this block will become how much? It will become this only. Okay, because these two are cancelling each other. So that will provide it with an acceleration. So this will become your answer. Okay, so is this clear, Anj? All right, so with that, we'll conclude today's session. Next time, we'll continue with more doubts in friction and a couple of doubts remaining in the cumulative test. Okay. Yeah, take it down, no problem.